Students, welcome to lecture number 30. So, we are slowly entering into the 30th lectures, and in another 10 lectures or so the course will be over. So, we have been discussing about the length scales in material systems, right. In the last lecture I started that discussion. Length scales are very important in material science. At the beginning it may not be clear that why we are bringing such discussions into a course in AI/ML, but slowly you realize that modeling using machine learning and deep learning will require data, and many cases today's world, I am not saying 20-30 years back, in today's world many cases the data are obtained from simulations or calculations. Calculation using computers, not by hand calculations, and the data will be used for modeling phase formation, microstructure understanding, and some cases even estimation of properties. So, under such a circumstances, how we will use this kind of data? So, length scale may start from atoms or electrons even, as I discussed in the last lecture, and it can go even higher as high as meter level for the components, right. So, if you want to develop a silicon solar panel for a kilometer long, so distance can even go even much larger than that, right. So, it is a massive scale from atomistic to the real applications, and how we can actually understand that, that is the purpose of this type of lectures. So, we will today start the very microscopic length scale, not nanoscopic or atomic level length scale, we will start on that. So, we are not going to discuss about what will happen in the macroscopic or even say meter or centimeter level length scale, because those will not be important for the design of materials. Those will be important for properties, I understand, but not for the design of materials. So, if I get time we will bring about that discussions, but otherwise we will mostly focus on our discussions on the microscopic, submicroscopic, atomic scale aspects of length scales. So, let us talk about this is the part 2 of the lecture series or lecture whatever 3-4 lectures we are going to spend on that. So, first begin with some recap. We started discussing about the gas turbine engines, which is one of the important system which is used in the aero engines for the whole world, right, and this is a classic example. This is a classic example in the sense that without this aero engine cannot function, and therefore you cannot have air travel. So, remember this, in the last century one of the major invention is the discovery of these aeroplanes. That is why you can fly from different distances, we can reach any part of the world in a 24 hours time duration, as well also we can use this in warfare, the military applications. So, major part of this is this turbine engine, and in the turbine engine important part is this blades which are attached on a, you can see that on this picture, attached on a rotor, and as I told you this rotor rotates very high RPM, sometimes 60,000 RPM. So, these blades are actually rotated by burning fuel, and the fuel burning will lead to gas formations. The kinetic energy of these gases which are impressed on these blades will have to rotate these blades, but obviously when the fuel is burned at high temperature, the material has to withstand that high temperature. Effect of high temperature in the sense of stress is a stress of oxidation, corrosion, all kinds of things. So, we use superalloys for that, and these alloys actually contain very large number of elements. There can be nickel base, cobalt base, iron base or many other types, but they contain large number of elements, that is why they are called superalloys. If you look at the picture on the right side, you see there is a temperature of the base metal in the gas turbine engine versus ER. We started with rod superalloys, temperature can go maximum 800. So, we are into this third generation or fourth generation of single crystal superalloys which can go up to 1100 degrees Celsius temperature, and we are thinking of having a jump because we are thinking of making supersonic jets which can fly 3 to 4 times or even 6 times, 7 times the speed of sound in the air, and that requires a completely different kinds of design of materials. So that is why I given these authors, Wright and Gibbons has given whether moly, silicon, boron alloys can be used or not. Well, that is a question, I will not discuss about that, but nonetheless single crystal superalloys blades can be used till about 1100 degrees Celsius temperature. That is a major discovery of 800 to 1100 Celsius in the last 60 to 70 years. So how this design has happened? The design was possible obviously not by machine learning, because in those days machine learning was not there. It was only possible by understanding the length scales, the microstructures, the phases, all these issues together. So as you see here, these plates can be either single crystalline, you can see here on the right side this is a single crystal blade, then you have a directionally solidified columnar grains, or you can have a equiax crystal structures. Obviously these kind of blades, DS solid structures or equiax crystal structure are used for ground based turbine engines, not for aeroplanes. Okay. So single crystal blades are normally used for aeroplanes, they look like this, they can be as long as a meter. So now what a kind of microstructure it develops, we talked about it, right. So you have base material and then you have top coat. Top coat is normally a insulating material which is like a zirconium dioxide with certain amount of yttrium oxide, that is because we have to stabilize the phase of zirconium dioxide. Zirconium dioxide has different kinds of phases, monoclinic, orthorhombic, cubic. So we have to stabilize the cubic phase, that is why 7% yttrium oxide is added, and this is directionally grown crystals of zirconium dioxide so that it can provide you maximum thermal resistance. But it has a different thermal expansion coefficient. Conductivity is obviously to be very low, of the order of 1 to 0.4 joule per meter per second Kelvin, okay, watt per meter per second. Okay. But it has a very different thermal expansion coefficient as compared to the superalloy. Superalloy is a metal, it is a metallic behavior, this is an alloy of different metals. So superalloy will have very high expansion coefficients compared to ceramics. So therefore if you hit if you are basically using in high temperature, there will be thermal mismatch, and this can lead to stress generation at the interface, and that can actually lead to failure. So that is why you have to put a intermediate layer which is called a bond coat, you can see here, and this bond coat has composition which is basically platinum, aluminum, many other metals, nickel, chromium also would be there, and this bond coat actually once it is subject to high temperature, it can form a thermally grown aluminum oxide. That is how this gradient of thermal expansion coefficient can be created from zirconium oxide to aluminum oxide to bond coat to the superalloy. This is a technology itself, that is not a very small thing to understand. You can see the length scale also. So the top coat is very thin, or not very thin, it should be hundreds of microns, and bond coat will be thin, it will be about 10 to 20 microns, and then superalloy blade is having certain specific structure. If you look at the microstructure superalloy, this has a gamma prime microstructure. So gamma prime has the majority phase here, you can see here this kind of structures are gamma prime, and gamma prime is the order structure of gamma. Gamma is a FCC nickel based structure, and where you have random arrangement of atoms in the atomic level. On the other hand, gamma prime will have specific arrangement of atoms, if stress center positions are occupied by the nickel and corner atoms are occupied by aluminum. Why? Because it is an Ni3Al structure. So therefore there are 3 atoms of nickel and 1 atom of aluminum in the unit cell. So it is only possible when you have 6 faces of these cubes are occupied by nickel atoms, and each corner will give you, or 8 corners will give you 1 aluminum atom. That is how the nickel 3 aluminum comes into picture. So now this microstructure can be looked at different length scale, like in SEM you can see there is a 2 micron, and you can see here. So the SEM you can look square structures, but still not very clear as in TM, transmission electron microscope. But one can even go down the length scale, look at the atomic level segregations. So this is a picture from 3-dimensional atomic probe, atom probe tomography. This is a tomographic things. You can clearly see between 2 gamma prime grains there is a boundary which is having lot of segregation of elements, right, and this is segregation of nickel actually, you can clearly see. So one can actually even look at the distribution of elements, which one is stabilizing the gamma prime phases and many other things. So we can also discuss what will happen in the bond coat, reaction layer, So, you can see here the reaction layer between this bond coat and the top coat will have gamma alumina like structure possible. That is a thermal oxide. You can also have this structure extended to the end of this or to the top of the bond coat, right. So, there are different kinds of microstructures can form, and these are the length scale issues we have to deal with it. So, one from SEM or optical micrograph, which has micron level resolutions, to SEM level where it can have actually tens of nanometer level resolution, to the TEM level which is about the close to 1 nanometer level resolution, and we are even going down to atom probe tomography level where we can have atomic level resolution, that is of the order of Armstrong level resolution. So, when you have lot of data, you should know these actually are nothing but a data, right. So, like in case of images, it is nothing but a data. I talked about deep dialing models and where these images can be used for modeling. So, these are nothing but data. In atomic tomography, we self generate data in terms of atom distribution, number of atoms. So, this actually need to be understood if you want to model this kind of aspects and bring a comprehensive picture of these structure stability of this kind of devices like aero engines. So, another important aspect I talked about is the aero body of the plane. As you know that plane was discovered is something at the beginning of the last century, 1901 to 1905. That time the Wright brothers, Oliver and William brothers, they actually discovered the plane first time. They have made it, invented actually we can say, and this is the picture of that taken from Wikipedia, and this is the picture of the modern planes in 1990s or 1980s actually, okay. So, the body of the material is basically duralumin, you know that. It contains about almost like a 4% copper, and rest is aluminum, a little bit of silicon, other things, okay. So, the alloy itself has undergone a lot of changes, chemistry changes. You can see here it can have tin, it can have magnesium, silicon, even silver, lithium can be there also. These are added to form different kinds of precipitates in the microstructure, and to form the precipitates you need to age it at different temperatures. As you see here, this is the hardness versus aging time. I do not want to go into what is aging, how it is done. You can look at my own course in on NPTEL on phase diagrams, where you will be, we have discussed about all these things, or at phase transformations. These courses you will be you can actually do it in next semester also, which where we will offer these courses. So, there we talk about what is aging, how aging is done. Nonetheless, the lectures of this course is already available online, you can go through it. So, aging is what is going to increase the hardness because of the precipitation of these phases, and as you can see depending on the alloy chemistry, aging can lead to different kinds of hardnesses. So, this is all taken from J.F. Nye, and this paper is discussed by John Allison, University of Michigan, as a part of TMS lecture. So, this is as you know that there is always a societal and global competitions which require us to do better material, cheaper material which can allow us to fly at a higher rate or speed. So, that is why we need to think about how to design materials in a pragmatic way. So, we can use approach which will start with atomistic, like unit cell, you have atoms, you can see here. That will allow us to use quantum mechanical treatments, where you can predict even stability of different phases and even their properties, and from that length scale we can even go to higher length scale. We can talk about phases and microstructures using phase diagrams. That is what we will discuss today. These are called calculated phase diagrams, and then from there we can actually talk about this diffusion, kinetics, aging behavior, all these aspects. So, this is the divide from atomistics to the macro scale. That divide needs to be bridged, and how we can do that, that is what is the discussion today. And in fact, the data you can always see in the metal handbook published by American Society of Metals, data on atomic scale, data on phase diagrams, data on microstructure, everything you can access using these handbooks. These are available even in terms of soft books or soft copies, you can access that. Another important example I gave you is this aluminum Ford castings. These car engines use aluminum silicon alloy, high pyrotechnic. You can see here something like about 11% aluminum silicon alloy is used. I mean to say weight percentage, not atom percentage. Atom percent will be, atom percent also 11% only. Yes, you are right. This 11.8% is something I would use, high pyrotechnic. That is the corresponding to 15% weight percent of the silicon. And this is what it will form a microstructure, aluminum matrix with aluminum silicon eutectic in which silicon is used as a plates, you can see here. So Ford, thanks to Ford, this slide can share with you, we should be able to correlate the properties of the car engine with the microstructure. So we can actually try to develop virtual aluminum castings using without doing any experiments. So in a real traditional product development, you always take some initial geometry, do some database of materials to measure the properties, and finally we can actually make the profile service of the predictive life service of this casting before making it, and then we do a model casting and check whether it is happening or not. This requires you to build the casting from the model, test it, if it does not work again rebuild it and retest it. That is quite time consuming, right, very time consuming thing. So modern days we do not want that, we do not want any kind of build, rebuild, test, retest, because we do not have much time to discover new castings or take it to the industry level. So what we can do is basically we can remove that part and we can actually have much more cyclic operation between this casting, the virtual casting which I just now talked about it, and the design. Design is on this first sector, you can see this is what is design is, and this is what is your virtual casting is, right. So between these two we need to have a more discussion, more talk, so that we can have many more cycles on that before actually we make the casting. So that is why we need to use data science, we need to use more of machine learning at different length scale, connect the microstructure, alloy chemistry and microstructure with the properties as well as the quality of the casting. That is the key aspects in today's world. In order to do that, we need to have a different kind of approach. So what do you do that? That is what is called processing structure property linkage. Remember my first 10 to 12 lectures from lecture number 3 to lecture number 14, there we have discussed about this structure property correlation with processing, right. So we have a chemistry of alloy, from that we can develop thermodynamical and kinetic models that will give us the phase diagrams as well as diffusion coefficients, which can allow you to calculate the reaction rates of formation of precipitates or different kinds of microstructure phases. And then we can actually, once you do that, then you can actually understand microstructure in the sense of porosities in the castings, eutectic phases as well as precipitates. From there we should be able to predict properties of the material, especially mechanical properties of high cycle fatigue, low cycle fatigue, yield strength as well as the thermal growth behavior of the precipitates. That is what it is, and we should be able to do heat treatment in a virtual level, not like a real experiments. Heat treatment means solutionizing treatment, aging treatment. So this is what actually we are, this is the dream actually of any material scientist. Whether we can do it or not, that is the question for the future, but this is something we are thinking of doing it. Whether we can take a cast aluminum casting and do this processing structure property linkage using models, and this requires you to understand the different length scales, starting from chemistry, thermodynamics, phase of microstructures, going down to atomic level, and then predicting the properties which we will finally getting, right. So material engineering is all about finding the best of all the combinations. So therefore we need to find a means to conduct these quantitative trade-offs between the processing structure properties. That is the very aim of this, and that is why new subject has started called ICME, and ICME requires you to understand all length scale integrated, we call it integrated computational materials engineering. For the car engine, you can see here, if you do a simple optical metrolography, you get this kind of grain structures which are of the order of 1 to 10 millimeters, very large, you can see by naked eyes. And then if you go down the microstructure length scale, we can see in ACM level the grains or microstructures like this, you can see about 10 to 500 microns, you can see aluminum dendrite, silicon, aluminum, silicon, eutectic, but you do not see precipitates unless until you go to the TM level. That is why you can see 1 to 100 nanostructure materials, and finally one can even go to high resolution microscope. This is actually high resolution TM microstructures, where you can see atoms of precipitates and the background structures. So what are the different things we can do, like in case of this kind of microstructures, like optical microscopy level, we can see the grains and microporosities. That will be important to predict high level, high cycle fatigue as well as ductility. And this is of the order of 1 meter long, engine is of the order of 1 meter long. So that is what the component is actually, and when you go down to millimeter, you are going down 10 to the minus 3 length scales. So once you go down from optical microlograph to SEM level, this is SEM level actually, this is we can say SEM, this is optical metallography, and this is your TM. So, in SEM level we can actually see the eutectic phases, dendritic phases, we can even see microporosities or even formation of any intermetallic phases are there or not, because you have silicon, aluminum and some amount of iron will be there because this commercial alloys, it can form intermetallics and they are important for determining the ductilities and other properties. So, what are the parameters we are interested? Yield strength, tensile strength, high cycle fatigue, low cycle fatigue, ductility, thermal growth, right. These are important at the length scale. Once you go to nanostructure levels, that is 1 to 100 nanometers in case of TM, then we are interested to measure the precipitates size, precipitates volume fractions as well as orientation of the precipitates. That is the key things when you determine the yield strength, tensile strength, low cycle fatigues, or even we need to also be interested to know that this how these precipitates will grow as a function of temperature, that is called thermal growth. Finally, you can go down to atomic level, there you will be able to find out the atomic structures, interface structures importantly between the precipitates and the matrix, as well as the properties like thermal growth, when these precipitates can grow nicely or not, what kind of atomic structures you require in order to stop the growth of the precipitates. That is what is important in superalloys. Superalloys do not allow the thermal growth of these gamma prime precipitates, right. That is why superalloys are very good at high temperature. So, but then for the cylinder block applications, temperatures may not be very high, maybe maximum 3 to 400 degrees Celsius temperature, but remember we are using aluminum alloy, melting temperature of the alloy is very low. So, therefore, the precipitates can grow under certain long thermal history during application of a car engine. This is again taken from John Allison's University of Michigan when he provided a lecture as a part of TMS. So, now the question is, if we look into details of the SEM microstructure, that is what I have shown you. You can also have aluminum dendrites, microporosities, silicon as a phase in the eutectic and some intermetallics you can see here, right. These are all there. So, we will be able to see that. Now, if you go down the microstructure, you can see even precipitates within this aluminum dendrites, L2 theta prime or theta precipitate is possible. Still, you can look at high resolution micrograph, you can see the atomic structures also, the layers of aluminum copper. Copper is looking like a bright layers, aluminum looking like a dark layers, you can see them also. This will give us important aspects of the interface between the precipitates and the matrix. So, these are all very subtle things in our discussions, and I just wanted to go back to this slide again. This is a simple microstructure, but you can see you can have a lot of data out of it. Aluminum dendrites, how they will distribute themselves, how they are going to be, because they are the ones to provide the ductility, right. Aluminum is a ductile phase, and within aluminum you have precipitates like this, which you cannot see under SEM, but they are there in the microstructure, they are different length scale. So, how they are going to affect your mechanical and physical properties like thermal conductivity, okay. Then a car engine thermal conductivity is important, yield strength or tensile strength or even your growth of these precipitates during the applications. So, all these are going to be obtained from detailed modeling of these microstructures at different length scales. These are the key aspects which you will be talking about it. So, let us start with the first thing. So, thermodynamics is the key aspects in material science, right, that provides you a bridge between what you can process and what you can get in the actual practice. So, when you are talking about what you get, we are interested in properties and performances, right. So, what are the properties you are interested? You are interested in mechanical, chemical, electrical, magnetic, thermal properties. I discussed some of these things actually, mechanical, electrical, magnetic properties in the beginning of my course. So, now these are the properties you are interested. So, these properties will depend on structure you develop. Structure means not only crystal structure, microstructure, macrostructures, phases, distribution, all these things will be determining these properties. So, therefore, we need to know atomic structure, crystal structure, grain structure, phase distribution, defect structures. Remember, we have talked about defect structure also, dislocations, twins, many other things. So, this bridge between these two are very important. Now, how do you develop these castings or whatever components? By definite processings. But during processings, we have different certain parameters to be controlled, like temperatures, pressure or stress, strain, and chemical composition of the material. That also we can change, right? Whether it is aluminum silicon, aluminum copper silicon, aluminum copper magnesium silicon, whatever we can change, right? That is also parameter in processing. So, in processing you have different kinds of techniques, but fundamentally you are varying temperature, chemistry, pressure, strain or volume. These are the 3-4 fundamental parameters we vary, but we can vary many other things. We can vary magnetic field also if your processing condition requires that. So, these are the different parameters from properties to structure to processing. Okay? You can see that actually. And remember, finally your game is to control the properties or achieve the best possible properties. So, how we can have a trade off between processing so that we can obtain the optimum structure. That is what it is, the key aspects of thermodynamics. So, thermodynamics is the basis for understanding the material response to change in temperature, pressure or composition. Thus, it is the critical link between the processing and the microstructure, and that is why you need to know this link very well. That is the key aspects in material science. If you do not know these links, you will not be able to predict properties and performances. Okay? So, as you understand, finally you are interested to control the structure from the properties, so that we can predict or we can target to achieve these properties which are required for the application. So, important aspect is the performance, whether you are taking an exam, your performance is important, or you are applying a material for real time application, performance is the key things, and there thermodynamics plays the very important role. So, we always do experiments, but experiments can be done to predict different kinds of microstructures. Experiments are done to get certain kind of informations, but we like to predict what kind of information we can get in experimentations. Often, let us say if I want to process an alloy by such way, some way, what kind of information I am expecting to get, can I do it using a modeling, so that we can have a lot of predictability. So, modeling can be done in terms of first principle calculations from atomistic, you can take atoms and electrons, the first principle calculation and predict that, or we can actually use microscopic things like CALFAT or calculation of phase diagrams to do that. So, and CALFAT can also have feed from statistical thermodynamics, meaning the functions which you will see can actually come from statistical thermodynamics. So, finally, it is an integration of these data science which we can obtain from CALFAT, first principle calculation and statistical thermodynamics will allow us to make a better predictions of the kind of microstructures and properties you will get after doing certain experimentations. Okay. So, when you talk about properties, what are the things we are talking about it? We are talking about having thermodynamic property like enthalpy, entropy, Gibbs energy or thermal expansion heat capacities. We also need to know about kinetic properties, because that is what is going to talk about thermal growth of precipitates or dendrites or the eutectics, right. That is what we talked about few minutes back, and that requires you to know the diffusion coefficients. We also need to know sometimes shear viscosity of your melt. Okay, that is the critical aspects when you make a casting, whether it is liquid of sufficient flow or not. So, then you have a mechanical properties as well as interfacial energies. Mechanical properties mean elastic properties, plastic properties. Interfacial parameters also very important, energies like for tracking faults, twins, dislocations, remember that we all talked about it. So, these are the things which we will be getting, this information which we will be getting from the calculations, and the calculations will lead to explosion of data, and this data will be used for prediction of things which we will get after experimentations or our processing conditions. So, this is what we are going to talk in the next part of the lecture, and in a much detailed manner, and we will start with the CALFAT today, so that we can understand the basic aspects of that. Let us stop here for the section part number 1, we come back with the part number 2.